Welcome to Computer Architecture. I'm Nachum Danzig. This is a guide to Lab 2.2, which involves multiplication, subtraction, addition. I teach at the Lave Academic Center in Jerusalem. Now here's the problem. Write a program for the implementation of a simple calculator according to the following rules. So it's going to say enter value. We're going to say input an integer. Then you're going to put in a number. You're going to put in a number. Then an opcode, which is either a asterisk for multiplication, a minus, a plus, or an ampersand for equals. In other words, I don't know why not use equals, but an ampersand to say finished. And then at the end of the program, it will print out the final sum. So I could do 7 times 3 plus 4 times 12 minus 2 plus 16, and I'd get the final result at the end. Now, we're not going to care about order of operations, because that would make it very hard. So we're just going to take the numbers as they come in and do a proper multiplication, subtraction, or addition. Now, there is one problem that could occur. Which is that there is such a thing as overflow. Now, when we multiply two numbers, each one is a 32-bit register maximally. In other words, theoretically, the person typed in a very large number to multiply against another large number. The largest number he could type in is a 32-bit, whatever the equivalent in decimal, the 32-bit binary number. But if he puts in two 32-bit binary numbers and he multiplies them, he's going to get a result which is obviously a lot larger than 32 bits. The maximum, in fact, will be 64 bits. And that's why we have a high and a low register. So let me go to a more detailed explanation about this. Integer multiplication. When we multiply two integers, for example, t0 and t1, where does the result go? So it goes into two registers, into low and high. But you can't access low and high directly. So therefore, we have a command called mflow and mfhigh. And if you type something like mflow, what it does is it takes the low portion, the low register, which is the least significant bits, the 32 right-hand bits, and there's the 32 least significant bits of the result. In other words, if the result that he did of his two numbers and he multiplied was 33 bits, then 32 of them will be in the low, and one of them will be in one of the digits, the 1 or the 0, will be in the high, because it'll have what we call overflowed out of, the result is longer than 32 bits, so some of it will overflow into the high register, along with the sign will be in the high register. Now, if the multiplication is small, let's say the result is it fits into 20 bits. So then the other bits of the low will be the sign of the number, which is 0 for positive numbers and 1 for negative numbers. And the high will also be the sign. The sign will continue into the high. So the high will be all zeros or all ones if it was a small number. If the number was larger, eventually the number gets so large that some of the value bits, some of the bits that represent value, get into the high section, and that's called an overflow. And that we want to detect. Because if that happens, we have really no way of printing the result. Now I will show you about how to detect that. For multiplication, we will never exceed the 64 bits provided by the two registers for the product, right? We'll never get more than 64 bits, but we could get more than 32 bits. However, we will want to know if there was an overflow from the low register to the high register, i.e., does the low register contain the entire result? That would be good if the whole register contains the entire result, or is some of the result in the high? To detect overflow to the high register, we know that for negative products in the low register, in other words, if the low register is a negative product, like negative 35 or negative 1,000,000, the high should be entirely ones. In other words, the high should be all ones, which means it's a negative number. Unless, when would it not be all ones? If some of the value that we computed of the product got into the high. That's an overflow. So whenever it's not all ones, we know there was an overflow. Now I wrote, it should be entirely ones or in 2's complement a minus 1. In other words, the minus 1, you should remember that the value minus 1 is all ones. In other words, negative 1 is represented in 32 bits by 32 ones. In 8 bits, negative 1 is represented by 8 ones. However many bits is your word length, that's how many ones you'd have to represent a negative 1 in 2's complement. For a positive product, the high should be 0. Otherwise, there has been some kind of overflow of the product again into the high register. Right? The high register should be showing that it's positive. If it's a positive number, it should be all zeros. So basically what we can do is we can check the result that we got. If it's negative, make sure that the high is the way it should be, which is all ones. And if we got check the result again, and if we got a positive result, make sure that the high is positive. Now there are other ways of doing it that people thought of which are not efficient but are possible. For example, you could check the two numbers that came in that the user gave you. He gave you, let's say, -5 and -6. So you know that since they're both negative, the result should be positive. And then check if the result, if the high bit, if the high is all zeros. And then if the signs of the two numbers that he gave you are not the same, then check that the high is negative, which is all ones. But it gets more complicated if you do it that way. My way is I ignore the numbers that he gave me, and what I do is I just check the result. I look at the result. If the result is positive, then the high better be all zeros. And if the result is negative, then the high better be all ones. So here's my algorithm if you want to look at it. It's if the low is positive, then if the high is not 0, then there was an overflow. Similarly, if the low, or inversely, if the low is negative, then if the high is not all ones, then it's overflow. Then you have an overflow. Now, why did I write all these ones here? That's how many ones I'd have to check. But instead of writing all these ones, you can just write the value -1, because the computer will convert a -1 into all those ones, because that's the value in 2's complement for a -1. So fine. So that's all you need to know. You need to know this. What's it called? This algorithm, this logical check. Do it this way, and you will have no troubles. There are other ways to do it. They'll be more difficult. So let's look at the program. So I'll go to New, create a new program, and I need to make my arrays. I don't really want to do that with you guys, but I'll do something like data, enter, let's call it enter num, and let's say it's of type ASCII, and let's say enter a number. And we might run another one. Enter sim for symbol dot ASCII Z, enter a symbol. Okay, we may have another one that your sum is, but I'm not going to do that right now. Now let's get to the program dot text, and I'm going to, well, the first thing I'm going to do is type out enter a number. So I have to put LA into A0. I got to make my pointer, and it's going to point to that string, and we'll enter num, and I got my pointer. And now I want to print it. Now, how do I print it? I got to look at my chart, and my chart tells me that to print a string is 4, and A0 has to be okay. Oops. Oh, I lost my. There we go. Okay. So I got to do li $v04, and then I got to do syscall. And if I run this, it's not going to let me. I got to save it. File, save as, and let's go to data MIPS. And I'm going to call it MIPS 2.2, save. And if I now run it, I'm going to get enter num. I like it on the same line. Okay. And if I run it, it prints enter a number like I wanted it to. Clear. I just like to check as I go. I don't like to write a whole lot of code and then nothing works, and I don't know why. So I wrote that, and I entered a number. Now I have to do another syscall. If we remember, a syscall for reading an integer is 5, so I'm going to have to do li vfs equals 5 load. That's read a number, and then I do syscall, and the number will be in v0. Now I'm going to also have to do a read in a character, which is 12. Read characters 12. So I'm gonna. Well, first of all, I've got the number now. I've got to have enter a symbol. So you see, it's going to get long, this program. And I'm going to have to copy this before I overwrite it. I'm going to have to copy this to, I copy with add, add $T1, $VFS, and $0. So 0 and the number he gave me is the number he gave me. And I'll store that in T1. And then I'm going to have to get the enter. Here, I'm not going to enter number. I'm going to write enter symbol. And I'm going to do print this thing. And then I'm going to do, again, I missed the syscall here. This is prints the string, prints it. Now I've got to do write the string, syscall. That's gonna accept the string from the user. Now I stored it. So let's do comments again. Print a message. That's these first 3 lines. Then receive the number. That's the second 2 lines. Now the number is in V0, so copy it into T1. Then print a new message. I got to put A0 to point to that, and V0 is that, and I've got to actually print the message. So I got to write syscall. Now I printed the message. Now I've got to accept a No, V0 has got to be 12. That's what we said. 12 is for reading a character, because I want to get a character now. What character do I want to get? Whatever symbol he gives me. And I got to do syscall. And now I got the character in V0. And I got to compare it. So how am I going to do that? Well, I'm going to have to create a bunch of characters. So let's do that way up at the top. And let's use, since we're using our A's and our V's and our T's. We use a T for that. So let's use the S's. So let's do like this. I can just simply go like this. LI $S0 at LI, load immediate. And I can put in it, for example, the symbol plus. And now, and I can do the same thing, LI $S0, the symbol multiply, for example. And now I can't do S0, I got to do S1. And the same thing for minus, and the same thing for strudel. And then I come over here and I can check BEQ if the thing that he gave me, which is in V0, is equal to plus. So, for example, plus. What am I going to write? $S0. If it's equal to 0, then go to a section which we'll call plus. And now I'll have a section called plus, and I'll have a section called mult, etc. And now in the mult, and I have a section called, sub, for subtraction. Now in the mult, I'm going to multiply the two numbers that he gave me, and I'm going to put them in the result. I've got to store them in this result, in the final product. By the way, if he types a number and then immediately types ampersand, like he's finished, then it should print out the number. So that means the number that I got here in the beginning, which I stored in T1, where is that? Here, in T1, in line 13, I stored it in T1. That number is the number I'm going to print. So I'm always going to be adding to that number. So it'll be T1 equals T1 plus T2. So that'll be like my store. Every time I get a new number, if it's plus, then it'll be T1 equals T1 plus, right? If it's add, it'll be something like add $T1, $T1, $T2, assuming that T2 is the next number. And then each time, so T1 will be the store. Now here I'm going to do multiply. I'm going to do mult T1, well, $T1, $T2. That was an S. T1. And then I've got to move from low into, well, the result should go into T1. And now what about the high? I got to check the high. I got to check now, is the sign of this, is this positive or negative, which is going to be, I'm going to use a set less than with a 0. And then I'm going to say, if it's less than 0, then check, then do a move. Well, I can anyway do a move from high, so I may as well just write it over here. Move from high, and let's store it in $T3. And now I'm going to check, is the high equal to this? So I'm going to do BEQ, and I'm going to have a register that has the value that I want to compare the high to. And I may have to do that twice. So, and then I may have to jump to some place if it is that. So that's the basic structure. I'm not going to solve the whole problem for you, but I think I've gotten you well on your way. Okay, guys, good luck.